Good morning. Welcome you all to the third part of the chapter Relations and Functions. In the last class, we discussed the theory part of relations in detail. In that section, we discussed what is an equivalence relation, equivalence class, and a partition of a set. Today, we are going to do some problems relating to that section. In this section, we include 6 questions, that is problems 1 to 6. You are not provided a special note, a separate note to write in your notebook. What you want to do is first see the question on the screen and write it down into your notebook. After that, think about the answer yourself. Then, listening my explanation of the answer, write the answer also to your notebook. That is the pattern of our class. Get ready? Question number 1. See the question and write the question in your notebook. Okay? The question is S equals at A, B, C, D. Write a relation on A which is reflexive only. That is the question number A. What is the set S equals at A, B, C, D? It contains 4 elements. To be a relation reflexive in this set, that must contains 4 elements. Which are they? AA, BB, CC and DD. Let me write it. Answer to question number A are equal to AA, BB, CC, DD. These 4 elements are compulsory to make a reflexive relation on the set. But see the question. What is the question here? Write a relation on A which is reflexive only, not reflexive. We want to write a relation which is reflexive only. For that, let us check whether this relation reflexive only. Is this relation reflexive? That is correct. What about the symmetry? This is symmetric and transitive also, because this relation is the identity relation. Okay. Here the question is we want to write the relation which is reflexive only. For that, we want to make this relation not symmetric and not transitive. Okay. To make it not symmetric, I am going to write an element that is AB. Okay. Now the relation is reflexive, not symmetric, because AB is here, BA is not here. What about the transitivity? Clearly, the relation is transitive. Why? AA belongs to R, AB belongs to R, then AB, it is again belongs to R. Another example, AB belongs to R, BB belongs to R, then AB belongs to R. Hence, this relation is transitive. Then what are the peculiarity of this relation now? Relation is reflexive, not symmetric, but transitive. What is the question? A relation which is reflexive only, so that we want to make it not transitive. For that, I am going to write one more element. Can you guess it? Yes, that is BC. Okay. Now, what about this relation? Is this relation reflexive? Yes. Is this symmetric? No. What about the transitivity? Clearly, the relation is not transitive, because AB belongs to R, BC belongs to R, and AC does not belongs to R. Therefore, this is an example for a relation on A which is reflexive only. You can find another such examples which is reflexive only on this relation. Find it. Now, let us discuss what is the answer to question number B. Write a relation on A which is reflexive and symmetric but not transitive. Here, in addition to reflexive, the relation we want to become symmetric. Okay. Then, write the answer. Answer to question number B. Only one example is enough. Then the relation must be reflexive. So it contains the elements AA, BB, CC and DD. Let me write. Then this relation is reflexive, symmetric and transitive, but the condition is that not transitive. For that I just write one element AB. When I write AB, I want to write BA also because the relation must be symmetric. Okay, then I write AB and BA for what? To make it symmetric. Now the relation is reflexive and symmetric. What about the transitivity? Yeah, transitive also. AB, BA belongs to R, then AA also belongs to R. Therefore this relation is transitive also. For that, in order to make it not transitive, I am going to add one more element. What is that? AC. When I write AC here, I want to write CA also in order to make it symmetric. Now what about the transitivity? Now here see BA in R, AC in R. What about BC? Is it in R? No. BA in R, AC in R, but BC does not belongs to R. Therefore this relation is reflexive, symmetric and not transitive. Therefore this is an example, this is an answer to the question number B. You can write another such examples yourself. Now let us discuss answer to question number C. What is question C? Write a relation on A which is transitive only. We want to write a relation which is transitive only. Okay, then let us think about a symbol, such as symbol example. Let R is equal to 5. Is the relation transitive only? That relation is transitive, at the same time symmetric. Therefore it is not transitive only. Therefore the relation must contain one element. Just write an example. R is equal to set AB. What about this relation? Is this relation reflexive? No, it is not reflexive because it does not contain AA. What about its symmetry? Is it symmetric? No. Why? AB belongs to R, BA does not belongs to R. What about the transitivity? Clearly it is transitive because we can't find two ordered pairs AB and BC in this relation such that AC does not belongs to R. Therefore this is an answer to the question. You can write another many such examples. Okay, answer to question number D. This is a very easy question. That is, write the smallest equivalence relation that can be defined on A. We discussed it in our theory section. The smallest equivalence relation that can be defined on A is the identity relation. AA, BB, CC, DD. Now answer to question number A is over. Write this to your notebook beautifully. Now let us move to question number 2. This is question number 2. Let A equals 1, 2, 3. Write an equivalence relation on A containing 1, 2 and 2, 1. Okay, pause the video, then write the question to your notebook. Okay, now let us move to the answer. Answer to question number A. What is question E? What is the answer to question number A? Write all equivalence relation on A. We want to write all equivalence relation on A containing 1, 2 and 2, 1. A is the set. To make an equivalence relation, that relation must be reflexive, symmetric and transitive. To make it reflexive, we want to write 1, 1, 2, 2 and 3, 3. Okay, let us start. R equal to, we want to write all the equivalence relation. Therefore I just write R1 in order to write R2 if there is another equivalence relation. Okay, R1 equal to, it must be reflexive because we are going to write an equivalence relation. Okay, for that we write 1, 1, 2, 2 and 3, 3 at first. Now let us check. This is reflexive, symmetric and transitive. Therefore it is an equivalence relation, but it does not contain 1, 2 and 2, 1. We want to write 1, 2 and 2, 1 in addition to 1, 1, 2, 2 and 3, 3. Let me write 1, 2 and 2, 1. What about this relation? This relation is reflexive, symmetric and transitive also. Therefore this is an equivalence relation containing 1, 2 and 2, 1. In addition to that, this is the smallest equivalence relation containing 1, 2 and 2, 1 on the set 1, 2, 3. Because if you delete any one of the elements out of this 5, this relation become non-equivalence. Suppose I am going to delete 2, 1. The relation is not equivalence because not symmetric. I am going to delete 1 1 1. Then at that time the relation is not reflexive because and hence it is not equivalence. Therefore this is the smallest equivalence relation having the given condition. Now let us check whether there is any other such relation. Let us write R2. Clearly R2 must contain these 5 elements because this is the smallest equivalence relation. Okay, I write that 5 elements. In addition to that, I am going to write one more element. Okay, 1 2 2 1, one more element, that is 1 3. Is this relation R2 equivalence? No. Why? It is not symmetric. 1 3 is here and 3 1 not here. So I just write 3 1 also. What about this relation? Is this relation reflexive? Yes. Symmetric? Yes. What about the transitivity? No. This relation is not transitive. Can you find the answer? Can you find the reason? Yes. 2 1 is here, 1 3 is here. But 2 1 is here, 1 3 is here. But 2 3 is not here. So I just, in order to make this relation transitive, I write 2 3 also. What about this relation? Is this relation symmetric? No. Because 2 3 is here and 3 2 does not present here. Therefore I just write 3 2 in order to make this relation symmetric. Now the relation contains 1 2 3 4 5 6 7 8 9 elements. 9 elements are there. The set contains only 3 elements. Therefore this relation is the universal relation A cross A. We know that A cross A is always equivalence. Therefore this is the second equivalence relation having the given condition. This is the smallest equivalence relation. This is the biggest equivalence relation having the given condition, and there is no need to search for another equivalence relation having the given condition because it is not possible. The reason is when we add any one element to the smallest equivalence relation, it becomes A cross A, and this is the largest equivalence relation on the given set. Okay, therefore this is the answer. Let us write what is answer to question number B. What is let us read what is question number B. Write all equivalence relation on A containing 1 2. Here in question it is mentioned only 1 2, but we know that when 1 2 present in an equivalence relation, it 2 1 also be there. 1 2 be an element, then 2 1 also be there in order to make it symmetric. Therefore these two questions are same. Then why they ask these two questions? We want to realize that these two questions are same question. Okay, then answer to question B, number B is just the same as that of question number A. Okay, answer to question number B and question number A are same. The reason is both questions are same. Then answer to question number C. What is question C? Write the or find the number of relations. We want to find the number of relations containing 1 2 and 1 3 which are reflexive and symmetric but not transitive. Reflexive, to be reflexive, it must contain 1 1 2 2 3 3. Just I write, and in question it is mentioned that the relation must contain 1 2 and 1 3. Therefore I just write 1 1 2 2 3 3, then 1 2 and 1 3 at first. Let us check. Is this reflexive? Okay. Is this symmetric? No. Why? 1 2 is here, 2 1 not here. 1 3 is here, 3 1 not here. So in order to make it symmetric, we want to write 2 1 and 3 1. Okay. Now the relation is reflexive and symmetric. What about the transitivity? Is this relation transitive? What is your opinion? No. Why? Listen, observe this ordered pair 1 3 2 1. We can write this 1 3 2 1 as 2 1 1 3 also. 2 1 1 3 because this is roster form. In roster form, the order in which elements are listed is not important. Therefore 1 3 2 1 is same as 2 1 1 3, and when BC belongs to R, AC must belongs to R here. Therefore we want to find 2 3 here to make it transitive. Clearly 2 3 is not an element of this relation. Therefore this relation is reflexive, symmetric but not transitive. Hence it is the required answer to the question. Okay, now let us check whether there any other such relation. Find the number of relations. We want to list all the relations satisfying the given condition. Okay, For that, we check for another relation satisfying the given condition. It must contain 1 1 2 2 3 3 because it must be reflexive, and 1 2 1 3 2 1 3 1 for symmetry. And let me write one more element to this set. Okay, that is 2 3. Okay, if I add 2 3 to this relation for searching for another relation, what we get? When we add 2 3 in the relation, to make it symmetric, I must add what? 3 2 also. Okay, now how many elements are there? 1 2 3 4 5 6 7 8 9. What is this? Across A. Across A is the universal relation. We know that it is equivalence, therefore we can't add. But the question is, the relation must not transitive. Equivalence relation is transitive relation, so we can't add 2 3 in this relation, and there is no a second relation satisfying the given condition. Clear? Hence the answer is, there is only one relation having the given condition. Okay, write it down your notebook beautifully. Then let us move to question number 3. This is question number 3. This is a relation in set builder form, and this relation is defined on a finite set, and hence the given relation is finite. We want to check this the reflexivity, symmetry and transitivity of this relation. Since this relation is finite, it is easy to write its roster form at first. For that, what is the relation here? 3x minus y equal to 0. We can write y equal to 3x also. We can give x is equal to 1 2 3 up to 14, but a condition is there: y must belongs to A. Let me give x is equal to 1 at first. When x is equal to 1, what is the value of y? Y equal to 3 into 1. 3 into 1 is 1 3. Okay. When x is equal to 2, what is y? 3 into 2, that is 6. 2 6. When x is equal to 3, 3 into 3, that is 9. When x is equal to 4, 3 into 4, that is for 12. Okay. When I give x is equal to 5 in this equation, what we get as y? Y equal to 3 into 5, that is 15. But we can't write that ordered pair here. What is the reason? 15 is not an element of A. To be a relation, it must be a subset of A cross A. If I write 5 15 here, it will not be a subset of A cross A, and hence we can't write for 15 here. Therefore the relation is over. It contains only 4 elements. Now it is very easy to check its reflexivity, symmetry and transitivity. You can say at a single glance. What about the symmetry? Is this relation symmetric? No, 1 1 is not an element of this relation, not symmetric. Sorry, not reflexive. What about the symmetry? 1 3 is here, 3 1 not here, not symmetric. What about transitivity? 1 3 is here, 3 9 is here, 1 9 is not an element of this relation. Therefore the relation is not transitive. Just let us write in a very simple way. Reflexivity, 1 1 is not an element of R, therefore the relation is not reflexive. And symmetry, 1 3 belongs to R, but 3 1 does not belongs to R, hence the relation is not symmetric. And the transitivity, that is 1 3 belongs to R, 3 9 belongs to R, but 1 9 does not belongs to R, therefore the relation is not transitive. Answer to question number 3 is over. Keep in mind that all the relation except x is equal to y, all the relation except x is equal to y, that is identity relation, are not equivalence. The only one equivalence relation in the form x plus by plus c equals 0 is the identity relation, x is equal to y. All other relations are non-equivalence relation. This relation is neither reflexive nor symmetric and nor transitive. Clear? Write it in notebook and move to question number 4. What is question number 4? R is equal to ordered pair x y such that y equal to s plus 5 x less than 4. This is the set builder form of the relation, and this relation is defining on n, that is the set of all natural numbers. There are 2 questions. First question is we want to show that it is not reflexive, and second question is check the symmetry and transitivity of R. Here the relation is defined on n, but one condition is that x is less than 4. Therefore it is easy to write its roster form at first. Okay, what is the relation? Y equal to s plus 5 and x less than 4. X must be a natural number, and that natural number must be less than 4. then which are the possible values of x? 1, 2 and 3. We can give x equal to 1, x equal to 2 and x equal to 3. Okay, when you give x equal to 1, what is the answer? 1 plus 5, that is 6. When you give x equal to 2, what is the answer? 2 plus 5, that is 7. When you give x equal to 3, 3 plus 5 is 8. And you can't give x is equal to 4 because there is a condition here. Okay, now this is the relation. Only 3 elements, containing 3 elements. What about this relation? Is this relation reflexive? No. What is the reason? The relation does not contain 1, 1. 1, 1 is not a member of this relation. Therefore, the relation is not reflexive. You can say the example as 2, 2 does not belong to R, 3, 3 does not belong to R, 100, 100 does not belong to R, 1000 does not belong to R, and so on. It is just enough to write a single example. A single example disprove a condition. Okay, to disprove a condition, to disprove a statement, it is enough to write a single example. What may be the example? No problem at all. Okay, now let us check the symmetry. Clearly it is not symmetric. What is the reason? 1, 6 is an element of R, but 6, 1 is not an element of the same relation. Therefore the relation is not symmetric. Very easy. Now let us discuss a transitivity. Okay, more attention is needed here, because when we say that a relation is not transitive, we want to find two ordered pairs AB and BC such that AC does not belong to R. Can you find such two ordered pairs here, AB and BC, and AC does not belong to R? For that, let us check AB ending with 6. Is there any ordered pair starting with 6? No. Is there any ordered pair starting with 7? No. Is there any ordered pair starting with 8? No. Hence, there is no two ordered pairs AB and BC here. It means that the condition is not satisfied, and there is no need to bother about the conclusion. Therefore, it means that we cannot find, there is no two ordered pairs AB and BC in this relation such that AB belongs to R, BC belongs to R, but AC does not belong to R. Trivially, the relation is transitive. Answer to question number 4 is over. Write it to your notebook beautifully. After that, let us move to question number 5. This is the question. Divisibility is the relation, and the set is set 1, 2, 3, 4, 5, 6. It is a finite set, and hence the relation is also finite. Here, answer to question number A. Question number A is, we want to show that the relation is reflexive and transitive. Okay, to show that a relation is reflexive, example is not enough. Okay, to show that a relation is transitive, example is not enough, but a general proof is required. Okay, can you say an element belongs to this relation? Y is divisible by X is the relation. Yes, 2, 4. One example is 2, 4. 2, 4 belongs to this relation. Y 2, 4 belongs to this relation. Y 4 is divisible by 2. 2, 6 belongs to this relation. Y 6 is divisible by 2. Okay, 1, 2 belongs to this relation. Y 2 is divisible by 1, and so on. Okay, now I am going to answer to question number A. We want to prove that this relation is reflexive. As I said earlier, a general proof is required. To prove that this relation is reflexive, we want to say that AA belongs to R for every A in capital A. It means that 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 belongs to this relation. Okay, in general, AA belongs to this relation. Clearly, AA belongs to this relation. Why? A is to XY be a member of relation, Y is divisible by X. AA be a member of this relation, A is divisible by A. That is correct. Every number in this set is divisible by itself. Therefore, A is divisible by A for every A in this set. Hence, AA belongs to R and the relation is reflexive. Hence, the relation is reflexive. Clear? Suppose I add the number 0 here. I add the number 0 here, 0, 1, 2, 3 up to 6. Then, is the relation reflexive? No, because 0 is not divisible by 0. Okay, at that time the relation is not reflexive. Hence, the relation divisibility is not a reflexive relation on the set containing 0. It means that this relation divisibility is not reflexive in the set R, set of all real numbers, Z set of all integers, Q set of all rational numbers, set 0, 1, 2, 3, 4, etc. Set of all whole numbers. This relation is not reflexive. It means, in short, if the set contains 0, the relation is not reflexive. Now let us check the transitivity. We want to prove that the relation is transitive. For that we want a general proof. AB belongs to R, BC belongs to R. What is the meaning? AB belongs to R implies B is divisible by A. BC belongs to R implies C is divisible by A. When B is divisible by A, B by A is a natural number in this set. Okay? We are considering this set, therefore B by A is a natural number. Clearly B by A is a natural number. For example, 2, 6 belongs to the relation. What is the reason? 6 by 2 is equal to 3. 3 is a natural number. In the same way, when AB belongs to the relation, B by A is a natural number. Let us name it as K1. Okay, B by A equal to K1. Okay, BC belongs to R implies what? C by B is a natural number. Let us call it as K2. B by A equal to K1 and C by B equal to K2. The next step we can write B equal to A K1 and C equal to BK2. And C equal to BK2. See, here B is here, B is equal to A K1 here. We can replace this B by this B. This is B, A K1. We can replace this B by A K1 in the next step. Okay, C is equal to A K1 K2. C is equal to B. Instead of B, I write A K1, K2. K1 into K2 is the product of two natural numbers. Therefore, it is a natural number. Let us call it as K. Then we get C is equal to AK. Okay, it means that C by A equal to what? K. C by A equal to K means C is divisible by A. Clear? C is divisible by A or AC. C is divisible by A or AC belongs to R. It means that whenever AB, BC belongs to R, then AC also belongs to R. Hence, the relation is what? Transitive. Therefore, the relation divisibility is reflexive and transitive on this set. When this set contains 0, this relation transitive, but at that time the relation is not reflexive. Keep in mind. Okay, now write the answer to question number B. Is this relation equivalence? For the relation to be equivalence, it must be reflexive, transitive and symmetric. Here the relation is reflexive and transitive. What about the symmetry? Let us check. Okay, symmetry of this relation. Clearly, 2, 4 is an element of this set. 2, 4 is an element of this set. What is the reason? 4 is divisible by 2. What about 4, 2? It does not belong to the set. What is the reason? 2 is not divisible by 4. 4 is divisible by 2. That is correct. But 2 is not divisible by 4. Therefore, 2, 4 belongs to R and 4, 2 does not belong to R. Relation is not symmetric. Not the color. The relation is not symmetric. And hence, it is not an equivalence relation. Then the relation divisibility is reflexive and transitive but not symmetric in the set 1, 2, 3, 4, 5, 6. Answer to question number 5 is over. Write down in your notebook. Now let us move to question number 6. There are two questions, and question A and question B. Both the questions are defined on the set R. What is this R? This boldface R, set of all real numbers. This R is the relation. Okay, this relation is defined on the set of all real numbers. Since this set is infinite set, the relation is also infinite. The relation contains infinitely many elements and we can't write it in roster form. Okay, now the question is, first question is, we want to check this relation. A less than or equal to B is reflexive and transitive. We want to show this relation reflexive and transitive and show that it is not symmetric. To prove the relation is reflexive and transitive, we want to make general proof. Okay, for to make not symmetric, example is enough. Clear? Answer to question number A. We want to prove that this relation is reflexive. When the relation is reflexive, AA must belongs to R. When AB belongs to R, A less than or equal to B. Then when AA belongs to R, A less than or equal to A. Is this statement correct? A less than or equal to A? Yes. The relation A less than or equal to A, the statement A less than or equal to A is correct. Why? It contains two statements. One is A less than A, or A equal to A. This statement is an or. This statement is a or statement. A or statement is true when any one of the statement is true. A less than A is false, but A equal to A is true. Means the compound statement is or statement. It is true. Why? A equal to A is true. Clear? A less than or equal to A is a true statement, and hence A less than or equal to A is true. Therefore, A belongs to R, and hence the relation is reflexive. Suppose this question is A less than B. Not A less than or equal to B, but A less than B. Then the relation is not reflexive. Why? A less than A is false. A less than A is false. If A less than B is the question, then the relation is not reflexive. Clear? Now, answer to question number B. Answer to next part, transitivity. We want to make a general proof. For that, to show that, to prove a relation is transitive, we want to take two ordered pairs AB and BC belongs to R. We want to show that AC also belongs to R. What is the meaning of AB belongs to R? A less than or equal to B. What is the meaning of BC belongs to R? B less than or equal to C. This both be are same. Therefore, we can write A less than or equal to B less than or equal to C. Okay? A less than or equal to B less than or equal to C. It means that A less than or equal to C. Very clear. Okay, when A less than or equal to C, AC belongs to R. When A less than or equal to C, AC belongs to R. AB belongs to R, BC belongs to R, implies AC belongs to R. Hence, the relation is what? Transitive. Then, A less than or equal to B, the relation A less than or equal to B defined on the set R is reflexive and transitive. When it is A less than B, that not reflexive but only transitive. Now, we want to disprove the relation is symmetric, that we want to show that this relation is not symmetric. For that, it is enough to take an example. Okay, you can say number of examples are there. For example, 1 3. 1 3 belongs to R. 1 less than or equal to 3 is correct, but 3 1 does not belongs to R. Why? 3 less than or equal to 1 is not correct. 3 less than 1 is false. 3 equal to 1 is false. Both statements are false. Therefore, 3 1 does not belongs to R. Hence, the relation is not symmetric. 1 3 is an example. You can take any example. 1 3, 1 4, 1 5, 200, etc. You can take any example satisfying the given condition. AB belongs to R and BA does not belongs to R. Anyway, this relation is not symmetric. Now, the last part, answer to question number B. Question is this: R in R, the relation is defined on R. A slight change is there in the relation. A less than or equal to B is changed to A less than or equal to B square. If A less than or equal to B square, the question is A less than or equal to B square, the relation is neither reflexive nor symmetric nor transitive. Okay, we want to show that this relation is neither reflexive nor symmetric nor transitive. For that, we have go through examples. Example is enough to disprove a statement. Okay, can you find an example to show that the relation is not reflexive? We want to set two numbers, both are same numbers, such that the number is less than or equal to square, it's square. The number is less than or equal to square. Suppose I take a 2. When I write 2 here, 2 less than or equal to 2 square, that is true. We want to get a false statement in order to disprove the reflexivity. Okay, think about it. Can you take a negative number? Negative 4. Then what we get? Negative 4 less than or equal to negative 4 square. That is negative 4 less than or equal to 16. That is again true. Therefore, this is not a counter example. Okay, then think about another example. Okay, think it. Yes, I think some of you find the answer correct. 1 by 2. 1 by 2. When I take 1 by 2 here, 1 by 2. 1 by 2 is a counter example, because 1 by 2 less than or equal to 1 by 2 square is false. 1 by 2 is half. 1 by 2 square is 1 by 4 quarter. Half less than or equal to quarter. That is a false statement. Hence, 1 by 2 is not a member of this relation. 1 by 2 is a real number, but 1 by 2 is not related to 1 by 2 in this relation. Therefore, the relation is not reflexive. You can take not only 1 by 2 but also any real number in between 0 and 1. Okay, 1 by 3, 1 by 4, 1 by 5, etc. These all are counter example to disprove the symmetry reflexivity of this relation. Clear? Now, next part, symmetry. That is very easy. You can very easily find the example. 1 3 example, 1 3 belongs to R, 1 less than 3 square is correct, but 3 1 does not belongs to R, 3 less than 1 square is false, therefore the relation is not symmetric. Very easy, no need of further explanation. What about the transitivity? A little bit difficult. Okay, so please listen carefully. We want to find two ordered pairs A, B and B, C in this relation, okay, such that A, C does not belongs to R. For that, it is easy to find, it is easy to write first AC, which is not in R. Here there is an AC. What is that? 3 1. 3 1 is not a member of this relation, okay. Then 3 is A and 1 is C. We want to write now two ordered pairs A, B and B, C both belongs to R. Okay, what is A? 3. What is C? 1. Then what is A, B? A, B is 3 and 1. B is here missing. Okay, that is that belongs to R, and B is missing. C is 1, belongs to R. Clear? Now this is AC. AC does not belongs to R. This is AB and this is BC. Now if we can find B, this B, this question mark, if we can find B, we succeed. Why? We find AB belongs to R, BC belongs to R, and AC does not belongs to R. At the first we want to find three ordered pairs A, B, B, C and AC. Now it is very easy. We want to find only B. Okay, now think about B. Which is the correct number we want to write here? Can we write it 2 here? 3 less than 3, 2, 2, 1. 3 less than or equal to 2 square. That is correct. 3 less than or equal to 4. But 2 less than or equal to 1. That is false. Therefore 2 is not a good example. 2 is not a correct example. What about 5? That is also wrong. Okay, what about 0? 3 0 belongs to R. That is wrong. 3 0 does not belongs to R. 3 less than or equal to 0 square is false. 0 is also a wrong example. Then which is correct? Can you guess the correct example? So many examples are there. Just I write an example, that is negative 4. 3 negative 4 belongs to R. That is correct. 3 less than or equal to negative 4 square. Negative 4 1 belongs to R. Why? Negative 4 less than 1 square. That is again correct. Okay, 3 negative 4 belongs to R, negative 4 1 belongs to R, and 3 1 does not belongs to R. 3 1 does not belongs to R. Now we found two ordered pairs A, B belongs to R, B, C belongs to R, and AC does not belongs to R. Hence this is a counter example. Don't by heart this negative 4. You can write any negative number. Any negative number here for B, which must be greater than or equal to square root of 3. Okay, which must be greater than or equal to square root of 3 because its square is less than or equal to 3. Clear? You can write any B, any negative number such that that negative number is greater than or equal to greater than means modulus value is greater than or equal to negative root 3. That is negative 4, negative 5, negative 6, etc. Okay. Now this is the example. Hence the relation is not transitive. This relation is neither reflexive nor symmetric nor transitive. Okay. Now today's class is over. Now think about next relation ordered pair AB such that A less than or equal to B cube. What about is it reflexive, symmetric, not symmetric, transitive? Also it is in the same way. It is not reflexive, symmetric and transitive. Check yourself. There is an assignment question to you. I will give you after next class the same question. Okay, hope you all use my class well. I am very happy to giving a chance to provide you these classes in a very easy manner, and I will be more delightful if you use these classes, learn well, study well and write the note well. Okay, if you find my classes beneficial to you, you don't forget to like, share and subscribe my channel as classes. Okay, thank you for watching. Waiting for next class. Goodbye.